we're going to determine the solution set. Given a replacement set, given the replacement set. We'll talk about what those mean here in a second. All right, so a couple things. You've talked about real numbers in junior high. We introduced you to imaginary so far. So in this case, 2.25, 2 1/4. So 2 1/4 is a real number. Another type of number it is, because it doesn't fit our whole numbers, right? 2 1/4 is not a whole number. It's not a complete number. It's 2 and then part of a number. So it can't be a whole number. It can't be a natural number. It can't be an integer. But it's also a rational number, because rational numbers are numbers that can be turned into fractions. We will do more with this at a later date. I'm just doing a quick run through real quick about what this is. All right, real numbers. The letter we use, because it says use the symbols, we use an R with a double bar, capital R, double bar. Since we already used an R for that, you got to think about what rational means. It means it can be turned into a fraction. A fraction bar is a division problem. And the result of a division problem is called the quotient. So they use the capital letter Q for that. On the next one, you actually have to know that you have the square root of 225, which we know is 15. You can use it in your calculator or look at your perfect square list. And so when we know that, that's clearly a real number. 15 is a real number. It's not a weird thing with a negative under the radical or anything like that. So we know it's real. We also know it's rational. I'm going to put a Q instead of R. A-T-I-O-N-A-L. It's an R. And we know that it's a complete number. So since it's a complete number, it fits other subsets. So not only is it rational, but it's an integer. It's a whole number. And it's a natural number. Natural numbers are the counting numbers, 1, 2, 3, 4, 5. Whole numbers are the counting numbers, 1, 2, 3, 4, 5, including 0 and their opposites. And then, whole numbers start at 0, sorry, and go 1, 2, 3, 4. Integers are made up of whole numbers and their opposites. I jumped ahead of myself there. We already talked about the R word. R for real. R with a double bar. We talked about rational as quotient. We'll come back to integer. It's a weird one. This one is whole, and this one is natural. And like I said, we're going to come back to this a little bit more later down the road. Just not the right time for it. Integer, they ran out of letters, so they used the letter Z. It stands for a German word meaning numbers. All right, let's look at the next one. There are two ways to solve this. One way that you would have not thought about doing, and then the way you probably are used to doing it from junior high. All right, so the most common way that people solve this equation is by distributing. So negative 2x, negative 2 times negative 3 would be positive 6 equals 10. Subtract 6 from both sides. So negative 2x equals 4. Divide by negative 2. Divide by negative 2. X equals negative 2. I'll blow this up a little bit so I can write better. I don't have enough space. Let me see if that gives me a little more room to write. Okay, the way you probably would have thought to do is, since this says negative 2 times something, if we do the inverse of times, we divide this side by negative 2. We got to divide this side by negative 2. So x minus 3 equals negative 5. I add 3 to both sides. So x equals negative 2 also. It doesn't matter how I solve it. I've done it correct both ways, just two different ways to think about it, which makes it nice to look at it from a different perspective. All right, so let's go ahead and define stuff. I'm going to change a word over here. I didn't like it after I typed it. Change this word right here. It says sentence again. I don't like to restate something with the same word when I'm defining something and I wasn't paying attention. So what the word is up here is an open sentence. is a mathematical where I had sentence, put statements, a mathematical statement that contains algebraic expressions and symbols. When I ask you to find the value for the variable that makes a sentence true, that is called solving the open sentence. So I'm asking you to find the answer while you're actually doing the technique called solving. All right, these are more specific types of open sentences. So an equation is an open sentence that contains an equal bar. So it has the equal bar on it. A sentence that contains these symbols, less than or equal to, greater than or equal to, less than or greater than, is called an inequality. You've worked with both. Nothing's new here. A set is a collection of objects, or in our case, since we're a math class, we're not collecting like piglets or buttons or stamps or anything like that. We're having a collection of numbers. So our collection of numbers, it's shown in a set of braces. Those are those squiggly braces, squiggly brackets. They look like this. I've seen them before. I don't draw them very well, but some people can draw them pretty. Each object in a set is called an element. So those are like the individual numbers within the set. The new words that you may not be familiar with are replacement set. The replacement set is a set of elements in which anyone may be used to take the place of a given variable or a placeholder in a mathematical sentence or expression, such as an equation or an inequality. So on your activity that we did, you had a set of keys. On that set of keys, you had numbers, right? So you tried every one of those solutions in there. You tried one of those replacement set values to see which ones actually worked in the inequality or the equation. Once you've tested all the values of the replacement set, the ones that actually work that make the sentence true is called the solution set. The solution set are the individual elements that create a true statement that makes an open sentence true. All right, so we're going to do a few examples. All right, so our keys are up here. These are that's our replacement set right there. And then 1, 2, and 3 here are our equations for this section. So we're literally going to substitute in the value and see which one works. So 2 times 0 plus 1 equals 5. Does the left-hand side equal the right side? Well, 2 times 0 is 0. 0 plus 1 is 1. Does 1 equal 5? And that is clearly not true. So then we try the next one. 2 times 1 plus 1 equals 5. So 2 times 1 is 2. 2 plus 1 is 3. 3 does not equal 5. So that is not a solution. All right, let's try 2 times 2 plus 1. Does that equal 5? So 2 times 2 is 4. 4 plus 1 is 5. 5 equals 5. So that's a hit. We got a good one. All right, let's try 3. 2 times 3 is 6. Plus 1 equals 5. So 2 times 3 is 6. 6 plus 1 is 7. Does 7 equal 5? No. All right, 2 times 4 is 8. 8 plus 1 is 9. Does 9 equal 5? No. So in this set, we use those squiggly brackets, those are called braces, and we put the solution that worked. Well, the only one that worked was the one where we plugged in 2. So 2 is considered to be the solution to that equation. All right, let's look at these guys, because these get a little bit different. So now I'm going to do the same set of keys up here. My replacement set is up here still. I'm going to plug in 2 times 0 and 0 plus 0. It's 2 times 0, 0 to 0 equals 0. Do 1, 2 times 1. And 1 plus 1. 2 equals 2. So everything's working so far. That's a check, that's a check. All right, let's do 2 times 2. Does that equal, let me erase that. Two times 2, does that equal 2 plus 2? So 2 times 2 is 4. Does 4 equal 4? That is a check. That is a solution. All right, let's keep going. 2 times 3 equals 3 plus 3. Is that true? That is true. So 6 equals 6. That's a check. Then the last one is 2 times 4. And does 4 plus 4 equal the same thing? 8 equal 8? Yes, it does. So that's a check. So actually in this solution set, the replacement set is the solution set. So we put 0, 1, 2, 3, 4. All of them worked. Okay? All right, let's look at this one. We're going to use the same set right here. We're going to plug in 0. 0 plus 2 equals 0. Well, 0 plus 2 is 2. Does 2 equal 0? Nope. All right, let's plug in 1. 1 plus 2. Does that equal 1? Does 3 equal 1? Nope. Let's do 2 plus 2. Does that equal 2? 4 equal 2? Nope. So you can probably already determine that if I put in 3, 3 plus 2 is not going to be 3. It's going to be 5. Does 5 equal 3? No. And then we have 3 plus, or not 3, we have 4 plus 2. Does 4 plus 2 equal 4? Does 6 equal 4? No. So this is considered to be no solutions in this set. So we do what we call an empty set. You might have used the circle with a slash, there's no solution, but an empty set means the same thing. This is called an empty set, meaning nothing worked. All right, let's look at inequalities. Same concept. This is your replacement set up here. You got to try them all out, see which ones work. Now, inequalities are a little different. You can have more than one answer. So let's plug in 0. What's 2 times 0 plus 1? Is that less than or equal to 5? Well, 2 times 0 is 0. 0 plus 1 is 1. Is 1 smaller than or equal to 5? That is a yes. Okay, try 2 times 1. 2 times 1 plus 1. 2 times 1 is 1. Or 2 times 1 is 2. 2 plus 1 is 3. Is 3 less than or equal to 5? That is a good answer. All right, let's do 2 times 2 plus 1. Is that less than or equal to 5? Well, 2 times 2 is 4. 4 plus 1 is 5. Is 5 less than or equal to 5? That is true. 5 is equal to itself. All right, now, as you can probably guess, if I put in 3, though, 2 times 3 is going to give me 6 plus 1. Is 6 plus 1 going to be smaller than 5? Well, 6 plus 1 would be 7. Is 7 smaller than 5? That is a definite no. All right, and then you plug in 2 times 4, and that's not going to work either because we're getting larger. That's not going to be give you anything equivalent. That's going to be 8 plus 1, which is 9. Is 9 smaller than or equal to 5? Absolutely not. So in this solution set, we'd put 0, 1, and 2, and then we close it back up, and that would be the solution set for that particular problem. get some other colors in here. Let's do an orange. All right, let's try this one. So now we're going to do the same set up here. Plug it in. So we have 0 plus 4. Is that smaller than 0? Well, is 4 smaller than 0? Obviously, no. Now let's put in 1. 1 plus 4 has to be smaller than 1. Is that going to work? Is 5 smaller than 1? No. All right, let's plug in 2. Is 2 plus 4? That gives me 6. Is 6 smaller than 2? Absolutely not. Plug in 3. Is 3 plus 4 smaller than 3? Is 7 smaller than 3? No. And then if we try 4, obviously 4 plus 4 is not going to be smaller than 4. So 8 is definitely not smaller than 4. So in this case, none of them work. So this is an empty set. No solution. None of them work. All right, last round. Same set of numbers. We're doing the same thing. Using the same replacement set to see which ones work. So we're just testing to see if an answer works. So we plug in 9. We have 9 less than or equal to 7 plus 2 times 0. Well, 2 times 0 is 0. Is 7, is 9 smaller than 7? No. Let's plug in 1. So we have 9 is smaller than or equal to 7 plus 2 times 1, which is 2. Is 9 smaller than or equal to 9? That is a true statement. All right, now we're going to plug in 2. And you probably see the pattern, since I'm going in kind of a sequential order. I go 0, 1, 2, 3, 4. You're going to see this value get bigger. All right, and if it gets bigger on the right, then we're going to be good. So we have 7 plus 2 times 2. All right, so 9 is less than or equal to 7 plus 4. What's 7 plus 4 give us? 9 is smaller than or equal to 11. That is a good statement. I'm going to go down here below. So I'm going to put in 9 smaller than or equal to 7 plus 2 times 3. And so we get 9 is smaller than or equal to 7 plus 6, which is 13. So 9 is less than or equal to 13. That works. And then last but not least, let's do the 4. 9, and we know it should work because it's getting bigger on the right side, which we want it to be bigger. 2 times 4. So this is 9 is less than or equal to 7 plus 8. What's 7 plus 8? 15. So 9 is smaller than 15 is correct. So in this case, all of the answers work. So 0, 1, 2, 3, and 4. All right, flip it to the back. We're only going to do a problem, maybe 2 on the back side here. Okay, on the back side, I just want to look at a couple of these in particular. I want to look at number 3 for sure. I can't get the paper to work right now, so it's somehow this keeps locking up on me. All right, so let's look at number 3. I'm just going to write it down this way because it's not letting me do much over on the other side. So our replacement set is 1, 3, 5, 7. And you really have to use your order of ops. And it says the equation is 2x squared plus 4 equals 54. All right, so apologies for the handwriting is atrocious right now because it's not letting me write very well. So we're going to plug in the different answers. So we're going to do 2 parentheses 1 squared plus 4. Is that going to get us close to 54? So first we do parentheses, nothing to do in there. Next we use our exponents. 1 squared is 1. 2 times 1 is 2. 2 plus 4, is that close to 54? No. So go to the next one. All right, so let's do 2 times 3 squared. Sorry, the green's not showing up. I'm just trying to do different colors so you can see me change my position. Is that going to get us to 54? So 3 times 3 is 9. 2 times 9 is 18. Is 18 plus 4 getting us to 54? No. So this one doesn't work. That one doesn't work. All right. To save time and my energy on this thing, the pen that's not working very well, let's jump to 5. Let's do 5, and then we'll talk about it. And then we're going to be done. So 5 times 5 is 25. That's what 5 squared means. 25 times 2, 2 quarters would be 50 cents. 50 cents would be 54. Does 54 equal itself? This is a check. That is a 4 at the end there. So this is good. If we did 7, I'll just do 7 real quick. Obviously 7 is going to be too big. So 2 times 7 plus 4. Well, 7 times 7 is 49. 49 doubled is 98. So we're already over the 54 mark. So 98 plus 4 would be 102. 102 does not equal 54.